All right, let's talk about the different shapes of distributions. So a symmetric distribution is what we looked at previously, right, with height. And symmetric distributions have the quality of the mean being equal to the median. They're symmetric because if this is the mean and the median, half of your data points will lie above that line and half will lie below the line. So it literally bifurcates the distribution into two parts, the upper and the lower. Now, the alternative to a symmetric distribution is a skewed distribution, and it could be a right skewed or a left skewed. A right skewed distribution occurs when the mean is higher than the median. Okay, you can see that here. And this is likely to happen if you have outliers on the high end of the data set. Remember, the mean is sensitive to outliers. The median is not. So if you have outliers on the high end, it's going to start to pull that mean above the median. An example of a right skewed distribution might be income, because you have some people that have extraordinarily high incomes and that pulls the average income up above the median. A left skewed distribution is just the opposite. This is where the mean would be less than the median. For example, here, the mean falls below the median, and that means you have outliers on the low end of your data set. Okay? An example of this might be human longevity, lifespan. And this is because we have infant mortality, that is, babies dying within the first year of life, which pulls down the average age of death, mean, below the median. Now, we can use visual aids to understand whether we have symmetric or skewed distributions. We can also use numerical, mathematical aids. And there's two that we're going to focus on. There's the Pearson's coefficient of skewness, which is through this formula here, and then there's Excel's coefficient of skewness. Now, the good news is you will never have to calculate this, okay? So don't worry about this formula, don't memorize it, don't even practice it. Excel uses that formula to create the output in its program. This one, however, is a more kind of crude measurement that can help us understand what skewness is. So you do want to understand this. And it's fairly simple. Let's do an example. Let's say we have a recent stats test for a class, and the mean was 72, the standard deviation was 4, and the median was 75. Okay? By using the Pearson coefficient of skewness, we would take the mean, 72, subtract the median, 75, and then we would multiply that by 3. Okay? And that should give you -9. Then you would take -9 and divide it by 4, and that will give you -2.25. So that would be our Pearson coefficient of skewness. How do we interpret that? Well, if you get a negative value, then you know that you have a left skewed data set, because the mean must be less than the median, which is the case here. 72 is less than 75. That's the only way you get a negative value. So that is a left skewed. Mean is less than the median. If you get a positive value, that means that the mean must be higher than the median, right? A positive value here, and that would be a right skewed, mean higher than median. And if the mean equals the median, you get a 0 in your numerator. So you get a symmetric distribution, right? A 0 is symmetric. So in essence, the Pearson coefficient of skewness tells us if we have a positive value, it's right skewed. If we have a negative value, it's left skewed. And if we have a 0, it is symmetric. Be aware, though, that it's a rare occasion that you get a mean perfectly equal to a median. That means that you would almost never have a symmetric distribution by this definition. But we use a more flexible type of analysis. And we say, look, if it's close to 0, if there is not a strong right skew or strong left skew, then it's presumably symmetric. Let's now talk about Shebachevs theorem. This theorem will allow us to estimate the percentage of our data that lies within a certain number of standard deviations from the mean. And its formula is as follows. It says at least 1 minus 1 over z squared of the items in any data set will be within z standard deviations of the mean, where z is any value greater than 1. So for example, if we want to know the percentage of items that are within 2 standard deviations of our mean in our data set, we'd plug in 2 here. Well, 2 squared is 4. 1 over 4 is 0.25. 1 minus 0.25 is 0.75. So 75% of our data must be within 2 standard deviations of our mean. Let's keep going. If we want to see what percentage of data that's within 3 standard deviations of our mean, we plug in 3 here. Well, 3 squared is 9. 1 over 9 is 0.11. 1 minus 0.11 is 0.89. So 89% of our data lie within 3 standard deviations of the mean. And then finally, if you want to do 4 standard deviations, z equals 4, you'd say 4 squared is 16. 1 divided by 16 is 0.0625. 1 minus 0.0625 is about 94%. So 94% of our data lies within 4 standard deviations of the mean. This is another way of understanding how our data is distributed. Now, Shebachevs theorem is very versatile because you can apply this formula to any data set, a skewed data set or a symmetric data set. It will work. Okay? The key is you can only apply it to standard deviations above 1. Now, if we know, however, that our data set is symmetrical, we don't need to use Shebachevs theorem. We can get a better understanding of our data set by using the empirical rule. But the key here is the distribution must be normal, aka symmetrical. The rule says that 68% of your data will lie within 1 standard deviation of the mean. It says that 95% of your data will lie within 2 standard deviations of the mean. And it says that 99.7% of your data, almost all of it, will lie within 3 standard deviations of the mean. We're just given these numbers. We don't have to calculate them. Now, let's compare these two to Shebachevs theorem. We can't compare this one because remember, Shebachevs theorem only works for standard deviations greater than 1. So we can't look at a standard deviation of 1 and derive a percentage. But we can compare this one and this one. So with Shebachevs rule, 75% of data values were within 2 standard deviations. But with the empirical rule, 95% of data values are within 2 standard deviations. With Shebachevs theorem, 89% of data values are within 3 standard deviations. But with the empirical rule, 99.7% of our data is within 3 standard deviations. So you would always prefer to use the empirical rule because within the same interval, you're capturing a higher fraction of your data than Shebachevs theorem would allow. The question is, are you dealing with a normal symmetrical distribution? Because if you're not, you can't use the empirical rule. You're forced to use Shebachevs. The real-world implications of this are important because let's say, for example, I'm studying grades at San Diego State University, and I collect the average grade. Let's assume that's a 3.0, and I find that the standard deviation is 0.5, right? Half a grade point. Well, if I don't know whether the distribution of grades at SDSU is normal, symmetrical, or not normal, skewed, then I'm forced to use Shebachevs theorem to understand that data. So if the mean is 3.0 and the standard deviation is 0.5, then I can say 75% of SDSU students have a GPA between 2.0 and 4.0. However, if I do know that the grades at SDSU are distributed normally, I can use the empirical rule. And I can say that 95% of students at San Diego State have a grade between 2.0 and 4.0. See what happened? I would much rather be able to say, based on my research, that 95% of students have a grade in that range versus only being able to say that 75% of students on campus have a grade within that range. So that's one of the important real-world implications of identifying whether you have a normal distribution or not. Okay, let's talk a little more about Z-scores. Z-scores show a position of data relative to the mean of the distribution. It indicates the number of standard deviations a value is from the mean. And here's the formula. It's actually a quite simple concept. Let's say I'm looking at an IQ, and let's say the average IQ x bar is 100. And let's say you have an IQ of 130. Okay? So you are essentially 30 IQ points above the average. That's our numerator. We know IQ has a standard deviation of 15. So 30 divided by 15 is 2, which means you would have an IQ that is 2 standard deviations above the mean, right? 130 minus 100 divided by 15 is 2. If you have a z-score of 0, it means that you're looking at a data point that is aligned with the mean. If you have a z-score that is positive, it means that you are looking at a data point that is above the mean. And if you have a z-score that is negative, it means you are looking at a data point that is below the mean. Okay? Just helps us contextualize where our data points lie in terms of standard deviations rather than the raw data. An example of this would be with IQ. IQ is often used to illustrate the normal distribution because we believe it is symmetrical in the human population. Let's say that we know IQ has an average and of course a median, because they would be the same, right, if it's symmetrical, of 100. And we further know that the standard deviation is 15. What would be the z-score for an IQ of 121? Yeah. Well, we would simply take 121, let me do this in Excel over here, okay. Put equals 121. We would subtract from that the mean, 100, okay. And then we would divide that, I need to put this in parentheses, and then we would divide that by our standard deviation, which is 15. Okay, so see the formula? And I get 1.4, which means that someone with an IQ of 121 is 1.4 standard deviation from the mean. Now, the other thing that this illustration shows us is our percentages, the empirical rule. Okay, is 68% and 95% respectively, and you can see that. So if we have a mean of 100 for IQ, we know that 68% of our data will lie within one standard deviation, one z-score. That means 85 to 115. And if we look at two standard deviations, z-score of 2, we would have 95% of our data, right? So the 70 to 130 IQ range. And then finally, of course, you can look at the 3 standard deviations, which would be 99.7% of the data. Okay, we'll stop there and pick up with covariance in the next video. Thanks.